Hello friends, welcome to my YouTube channel. The title of my today's video is Every real polynomial of odd degree has at least one real root. In this video, we show that every polynomial whose coefficients are real numbers and whose degree is odd has at least one root which is a real number. We need some prerequisites. We start with definition of continuous functions. A function f from R to R is said to be continuous if the following condition is satisfied at every point R lying in the real line. Given any epsilon greater than 0, there exists a delta. This delta depends on epsilon as well as on R, such that distance between fx and fr, that is absolute value of fx minus fr, is less than epsilon if the distance between x and r is less than delta, where r is any real number. Geometrically, it means that the graph obtained by plotting the values of fx against the values of x has no breakage. It is a single piece. That is, the graph has no breaks. If f and g are two continuous functions, then it is easy to see that the following functions are also continuous. What are those? One is the sum function. S from R to R given by Sx is equal to fx plus gx for all x in R. F and g are continuous. So, if we define a function s like this, it will also be continuous. And another one is the product function p, which is given by px is equal to fx multiplied with gx for all x in R. So, this is called product function, and if f and g are continuous, p is also continuous. Two of the most basic but fundamental examples of real valued continuous functions defined on the real line are as follows. First one is the identity function I from R to R given by Ix is equal to x. This is a real valued continuous function on R. And the other one is constant function C from R to R given by Cx is equal to small r for all x in R, where small r is any given real number. These two continuous functions along with the sum and product functions can be applied repeatedly to show that the polynomial function f from R to R given by fx is equal to a0 plus a1x plus dot dot plus an x to the power n, where n is a natural number and all these ai's are real numbers, is continuous. So, those sum function and product function and identity function and constant function can be combined together and applied repeatedly to show that this polynomial function is also continuous. Okay, it's not very difficult. Another interesting feature of the real valued continuous functions on the real line is as follows. If f from R to R is continuous and fr is not equal to 0, for some r lying on the real line, then there exists a delta greater than 0 such that fx and fr have the same sign for all x lying in the open interval r minus delta comma r plus delta. So in this open interval, fx and fr have the same sign. If fr is negative, fx is also negative. If fr is positive, fx is also positive. So this is same thing as saying fx into fr is greater than 0. That means these two quantities have same sign. In other words, a real valued continuous function on the real line preserves its sign in a small neighborhood of each of those points on the real line, which doesn't go to 0 under the function. Okay. This feature plays a crucial role in establishing the following famous theorem of Bolzano, which is also known as the intermediate value theorem. What is it? This is the one, Bolzano's theorem. If f from R to R is a continuous function and fa and fb have opposite signs. See here, if fa is positive, fb is negative. If fa is negative, fb is positive. So they have the opposite sign. So that means their product is negative. So if f is a continuous function and fa and fb have opposite sign for some ab on the real line, then there exists a real number small r between a and b such that fr is equal to 0. So if fa and fb have opposite sign, then there is an intermediate point which goes to exactly 0 under f. In other words, Bolzano's theorem says that we cannot draw a continuous curve in the xy plane starting from a point lying below or above the x-axis to a point lying above or below the x-axis without crossing the x-axis. That means we cannot jump x-axis. We have to cross x-axis if we want to reach from a point lying below the x-axis to a point lying above the x-axis. Okay. One more real valued function which we are going to make use of is the following sine function defined on the non-zero reals. What is it? The sine function, which is also denoted by SIG and sine from r minus 0, so non-zero reals, to r is given by sine x is equal to x by absolute value of x, which is equal to 1 if x is positive, minus 1 if x is negative, for all x in non-zero real line. Okay, non-zero real numbers. Clearly, this sine function is distributive over multiplication. Sine of the product of two non-zero real number is same as product of the sines of the two non-zero real numbers. We now state and prove our main result. Theorem. The polynomial a0 plus a1x plus dot dot plus an x to the power n, where n is a positive natural number, where n is a odd natural number and a0, a1, an are real numbers with an not equal to 0, has at least one real root. So what is the theorem? A polynomial of this type where n is an odd natural number, it's an odd number, and these ai's are all real numbers, and n is non-zero. Okay, so this highest degree coefficient is non-zero. So therefore, it is a odd degree polynomial. Then such a polynomial has at least one real root. Proof. Consider the function f from R to R defined by fx equal to that polynomial a0 plus a1x plus dot dot an x to the power n for all x in R. So this is a polynomial function. And we have already noted earlier that f is a real valued continuous function on the real line. It can be constructed using continuity, it can be constructed and its continuity can be proved using identity function, constant function and sum function, product function, and applying them repeatedly. If x is not equal to 0, then we can write, see here fx is that polynomial, so we can take an x to the power n common and whatever is left, that is written inside a square bracket. So last term is a to the power n x to the power n only, so that will give you 1. The remaining term I call it gx. So gx is actually equal to a0 divided by an x to the power n, a1 divided by this, an minus 1 divided by an x. Clearly, limit of gx as x becomes numerically large is 0. So limit of this gx tends to 0 as x become numerically very large. Okay, because as x tends to infinity, mod x tends to infinity, this will tend to 0, this will tend to 0, this will tend to 0. So everything will tend to 0. So there exists an m such that whenever absolute value of x is greater than or equal to m, the absolute value of gx is less than 1. Okay. By choosing numerical value of x sufficiently large, we can make absolute value of gx sufficiently small. So we want to make it smaller than 1. So there exists m satisfying this. Therefore, we have in particular, if I take x is equal to plus m or minus m, then this g of plus minus m is less than 1 and at the same time it is greater than minus 1. Therefore, g plus or minus m plus 1 is always greater than 0 because this quantity is greater than minus 1. So, this plus 1 is greater than 0. And what about the sign of this f of plus m or f of minus m? What is fx? Fx is this. So, f of plus m or f of minus m is an, in place of x I write plus m or minus m to the power n and then g plus m or minus m plus 1. So, that is what is written here. So, sign of this quantity is what? An plus minus m to the power n, g plus or minus m plus 1. Okay. Actually, two sets of equations written in one go. One is for plus m, another is for minus m. Now, sine function is distributive over multiplication. So, sine function gets distributed over this product. So, it is sine of an and sine of plus or minus m to the power n means sine of plus or minus m whole thing to the power n. And this quantity is always positive. That is what we have seen here. This is always positive. Therefore, its signature is sign is always 1. Its sign is always 1. So, we can forget it. This is into 1. And this one is sin n and m is positive. So, sine of plus or minus m is actually equal to plus or minus 1. If I take sine of plus m, that is same as 1, and if we take sine of minus m, it is minus 1. Since m is positive, plus m is positive, minus m is negative to the power n. And again n is odd, so plus minus 1 to the power n is same as plus minus 1. So therefore we see that sine of f of m is equal to sine of an and sine of f of minus m equal to minus sine of an. That means f of m and f of minus m have opposite signs. Thus it follows that f of minus m into f of m is less than 0. That is, the real valued continuous function f has opposite signs at the points minus m and plus m on the real line. Okay. So we get it from here. So now we can apply Bolzano's theorem. Hence, by Bolzano's theorem, there exists a real number between minus m and plus m such that f are equal to 0. So this r is that real root of the polynomial. Okay. This completes the proof. Thanks for watching.